All right, hello everyone. My name is Audrey Rosevear, and today I'm going to be telling you about minimal genus in four manifolds with circle actions. This is part of my senior thesis project advised by Weimin Chen at UMass. So we're going to be doing topology, and if you're not familiar with that, it's a field concerned with geometric objects, but only up to stretching and squishing operations. So for example, you see in this diagram, in each column, you have three objects that are considered the same topologically because you can deform one into another. Now, for this talk, we're really only going to be concerned with smooth objects, such as, in this case, smooth surfaces, ones where there's a well-defined tangent plane at each point. So this corresponds to the bottom two rows. We're not including the top row. And the surfaces here, compact orientable surfaces, are classified by their genus. That's the number of holes in the surface. So you see here surfaces of genus 0, 1, and 2, respectively, and the topological deformations that classify them equivalently. So we're going to be more interested in higher dimensions, 4 specifically. But the question we want to ask is, what topologically distinct ways can you have surfaces living in higher dimensional spaces? So our setting is manifolds. These are spaces that are nice enough for calculus, and you can define a sort of generalized multivariable calculus for them. For example, surfaces are two-dimensional manifolds, and we're still considering them up to stretching and squishing. And solving this problem will help give us some insight into the internal structure of our space and also help distinguish manifolds that in other ways seem topologically similar. Over the next few slides, we're going to formulate this precisely. And for that, I want to talk about homology. A class from a surface into a manifold carries something called a second homology class. I won't really go too deeply into what that is, but homology is an equivalence class. So a homology class can be carried by many different maps and surfaces into your manifold. And we can consider the set of all second homology classes, and we get a Z module. That's a type of vector space-ish thing, but instead of over the real numbers or complex numbers, we are over the integers. It's called H2M. In this definition, the image of the map from the surface to the manifold can intersect itself. It can fold over itself in any number of different ways. It still carries a second homology class as long as it's continuous. We're going to be interested in those maps which don't intersect themselves and which are differentiable. So these are smooth embeddings. And these define a two-dimensional submanifold of your larger four-dimensional manifold. So what we're really doing is looking at the structure of possible two-dimensional submanifolds in your four-dimensional manifold. So here's an example, and this is going to be a running example we'll come back to over the course of this talk. So our manifold is going to be a product of a surface of genus G and a torus. That's the surface of genus 1, and it's the product of two circles, where here the circle S1 is considered as the unit circle in the complex numbers. And we're really considering any manifold which is topologically equivalent to this manifold. Standard computations in algebraic topology show that H2M is equal to 4G plus 2 copies of Z. We won't really need that here. I just wanted to show you what this thing might look like. The class that we're going to be interested in is the class sigma carried by the natural embedding of the surface of genus G into M, where we're going to take any point P and just put it in there. And for any P, the homology class will be the same because you can just slide this thing around. So topologically speaking, it is the same. For an example of a non-embedded class, and this is going to represent a different homology class, we have a torus being embedded by taking your two angular coordinates in your circle and putting them into your second torus in M, but doubling the angle. So this is going to wrap twice around each of the two circles in M. And this represents a very different homology class, but it's not an embedded representation. Now, every class can be represented by an embedding, just not necessarily by a torus. It may have to be a surface of higher genus. So that allows us to formulate the exact problem that we're trying to solve, which is called the minimal genus problem. Given a homology class, what is the minimal genus of embedded surface which carries that class? So we just saw some examples, but it's not obvious whether or not they can be represented by, for example, a sphere. Once you've solved this problem, you get to map the complexity function from your second homology into the natural numbers. And so our goal is going to be to study the properties of this map. So why are we doing 4 dimensions? I did mention that earlier. In greater than 5 dimensions, this is not interesting. There are a few reasons for this, and it's a little subtle, though. One is that if your manifold is simply connected, whatever that means, this will vanish identically. In dimension 3, you can take a slight modification of this function, and you get a semi-norm, the Thurston norm. So a semi-norm, by that I mean it scales along integers and it satisfies the triangle inequality. So algebraically, this has some very, very nice properties, and we know a lot about this. We have connected it with many different areas of 3 manifolds. We can generally compute it in a given case. It's a very, very nice and well-studied object. In 4 dimensions, this is very, very difficult. We have some cases where we completely know the complexity function. Our really only tool to systematically study this is Seiberg-Witten gauge theory, which I'll get to in a minute. And with it, what we usually do is obtain lower bounds. Obtaining actual equality requires producing surfaces which satisfy these lower bounds, and we can't always do that. So even when we do have a systematic way of attacking it, the information we get is somewhat limited. So let's return to our example. Sigma carried by the surface of genus G embedded in our product of the surface and the torus. So just by our definition of sigma, we know it's carried by a surface of genus G, this surface right here. Now we can carry this class by surfaces of higher genus by, if you imagine taking your surface and adding on little handles to it to increase its genus, but small enough that they don't really go anywhere interesting in the manifold, that's going to represent the same homology class. So that map would carry the same class. So we can definitely do higher genus. Can it be carried by surface of lower genus? I don't know of any good way to solve this without appealing to the very technical methods which I'm about to introduce you to. It might be able to be done for this particular class and this particular manifold, but for those of you more familiar with algebraic topology, I recommend thinking about how you might solve this, and I hope you will be convinced that in general, this is a very difficult problem. So before we jump into the gauge theory, I want to tell you some quick facts about homology that we'll need. So in 4 dimensions, we have an algebraic object called the intersection form. That's a bilinear form that outputs integers on the second homologies. We denote it by a dot product. Roughly speaking, this is the signed count of intersection points of any surfaces carrying your 2 homology classes. It turns out that if you count the sign appropriately, this won't depend on which surfaces you use. So we'll be using that. We'll also be using this connection with analysis via de Rham cohomology. You take a closed 2 form, which is a sort of generalized vector field to higher dimensional manifolds, and you obtain a homology class called the Poincare dual. And this should give you a sense of how analysis might enter this. If you can use calculus to understand your closed 2 form, then you can understand things about the homology class. And that is the strategy we're going to take. So we're going to be looking at geometry and topology. As I said, topology is the study of things equivalent under deformation. Geometry is where you don't consider that equivalence. So given a topological object, we can talk about a geometric configuration of that object, which is going to be a specific representative of its topological class. This is equivalent to the specification of something called a metric, G alpha beta. I won't tell you what the metric is, but what it does is it gives you notions of angle, distance, area, etc. in your manifold. These are decidedly not topological invariants, but we can use them to do things that really start to look like geometry. There are a lot of connections between geometry and topology. I won't tell you a lot of them in depth, but this is very well studied and has spawned many different fields of math. For example, you can use analysis to link closed-2 forms that I mentioned earlier with properties of the metric, such as the curvature or the volume. So what we're going to be doing is studying closed-2 forms via the Seiberg-Witten equations. So this is a pair of nonlinear first-order elliptic partial differential equations arising from quantum field theory. If you aren't familiar with a lot of those buzzwords mean, first order only involves first derivatives. That's very good. Elliptic is a very, very nice class of partial differential equations to work with. Nonlinear is bad, but the nonlinearity here is somewhat mild. So if you look at the equations, you have something FA, the curvature of A, that's a linear differential object, first derivative. You have Q of psi here is your spinner. That's quadratic, 0th order, doesn't involve a derivative. And then you have psi lies in the kernel of this differential operator called the Dirac operator. It depends on A, and it roughly looks like a sum of first partial derivatives. The important thing to know here is that FA, the curvature of A, is a closed-2 form, which, as I said earlier, gives you a homology class. So if you can produce a solution to this, by studying the behavior of the solution, you can learn things about the homology class it represents. So what are the difficulties here? Well, to write these things down, you require a metric, and it's highly dependent on the metric. So if you are given solutions for a particular metric, it is never guaranteed that you will have solutions if you bump the metric a bit. One approach to get around this is to define the Seiberg-Witten invariant. This is a sort of signed count of your solutions, which turns out to be invariant under the change of metric. So this is how you do guarantee that there are solutions. This is a full-on topological invariant. And if your Seiberg-Witten invariant is non-zero, then that means there is at least one solution for any metric. Problem is this invariant very frequently vanishes, even when there are solutions. It's a signed count, so you may have solutions canceling out. So why do we want solutions? What can we get with the solutions? So for a particular metric, depending on a specific surface, if you find a solution for that metric, you can do some careful analysis on FA, your closed-2 form, to get a purely topological expression for a lower bound on your genus. This is what I referred to earlier. This is called a generalized adjunction inequality. So if FA represents a class K and if you have a solution for a certain metric, then you get this purely topological formula for a lower bound on the genus in terms of the intersection form of sigma with itself, and then another intersection between K and sigma. So this is generally, the right-hand side, very easy to compute with some basic topological things. So this is a very easy theorem to use. The problem is it's very difficult to find a solution for a metric unless your Seiberg-Witten invariants don't vanish. So in 1997, Peter Kronheimer tackled a specific type of form manifold, those that are a product of a circle and S1. if sigma has genus G and carries a class sigma, you get this type of adjunction inequality where your intersection term is replaced with the Thurston norm of the projection. You can take a class and you can project it down into three-dimensional space. You can take its Thurston norm. I said again that this is quite easy to compute in most cases. And so here we have another very easy to use theorem. Though it doesn't mention Seiberg-Witten equations at all in the theorem, it is proved using Seiberg-Witten theory in the argument that I outlined above. It doesn't require non-zero Seiberg-Witten invariance. Instead, it constructs the solutions for the appropriate metrics more directly. So back to our running example, product of a surface and a torus. Well, the torus is two circles, so we can take a surface and a circle. And we can look at the projection down of the class, which is still just going to be carried by the natural embedding of the surface in your three-manifold. By standard three-manifold techniques, you can show that this does minimize the genus in its homology class. And so by Kronheimer's theorem, we can run this to get the reverse inequality holds true, and then we can calculate the complexity exactly to be equal to G. So as I said, straightforward to use, but very difficult to prove. So the question is, can we generalize this to a broader array of situations? So suppose M is a four-manifold with a smooth action of the circle group S1. If the action is free, i.e. it has trivial stabilizer, you can take a quotient like you do in group theory, take equivalence classes that has the natural structure of a three-dimensional manifold. The basic example is n cross S1 mod S1 is equal to n. But in general, you can have a twisted product of n and S1 that will be M. And so this gives you a much more general class of manifolds that is a direct generalization of the product manifold. In a pair of papers, 2014 and 2016, Friedel, Vidusi, and Nagel considered this case and let its quotient n satisfy some semi-restrictive properties. A large class of n, but certainly not all the ones that one would want to consider. But they proved the same adjunction inequality using the projection. And so this is a very powerful theorem for any manifolds that you can use it for. The argument is very different than Kronheimer's. It requires non-zero Seiberg-Witten invariance, which is why the restricted hypotheses. And for certain Seiberg-Witten invariants, because you can just define them on three manifolds as well, you can lift them up to 4 dimensions using a theorem of Baldridge. After some topological fiddling, you can obtain this result. So all of these are for a class of manifolds called irreducible, but we would like to generalize Friedel and Nagel's result to all irreducible three manifolds because they're restricted in what kind they consider. So it's known by some pretty high-powered three-dimensional techniques that solutions to the Seiberg-Witten equations always exist on an irreducible three-manifold. Baldridge, the paper mentioned earlier, proves that you can lift the Seiberg-Witten invariance by lifting the solutions themselves. However, this only works for certain metrics. For certain metrics on your 4-dimensional manifold, you can lift your solutions from 3 dimensions to 4 dimensions. Now, that is very nice, but it doesn't give us solutions for the metric required by the adjunction inequality. So our current approach is we're trying to use a new-ish type of invariant called the family Seiberg-Witten invariants, which are invariants calculated for a family of metrics instead of all metrics. And this family includes the one that we want. So if we can prove that these are non-zero, we get solutions for the metric we want. This is a work in progress. The family Seiberg-Witten invariants are highly, highly technical, but we are hopeful that this will allow us to construct solutions for a broader class of manifolds and prove this adjunction inequality to obtain minimal genus for a number of manifolds with free circle actions. Here are my references. Thank you for watching.